Furthermore, in addition to brilliant and monstrous, the first worlds detected by the James Webb Telescope in the depths of space present serious problems for specialists. In detail, it is highly unlikely that worlds this large could exist so soon after the Big Bang. But this is not a surprise, as when Webb conducted observations on the puzzling discrepancy in the Hubble constant, it confirmed that the rate of expansion of the universe is actually much higher than it should be. But how can we explain this mysterious anomaly? Well, the simplest explanation is that our universe is just one among many, and that cosmic worlds are merging. What initially seems like a fixed idea from a creative sci-fi author is actually the hypothesis of an official study, the results of which are increasingly coherent with observations in space compared to the standard cosmological model. No James Webb Telescope will be helpful. Regardless of how powerful the space telescope we send into space is, we will never be able to see beyond the limit of the observable universe. This is because the universe is isotropic, meaning it appears the same to an observer regardless of their point of observation. There is a spherical space around our Earth that defines our cosmic field of vision. The fact that our view of the stars is limited and at childlike distance is due to the expansion of the universe. However, the universe does not expand into existing space. No, it is rather the space itself that is constantly growing. As a result, we cannot determine the distance to the observation horizon by simply multiplying the age of the universe by the speed of light. In fact, if we take cosmic expansion into account, the distance is not 13.8 billion light-years but 46.3 billion light-years. And in reality, the distant structures that mark today's visual barrier were only 40 million light-years away from us when they emitted their light. However, because the light currently emitted from there cannot simply reach us, we do not know what processes are currently underway there, or what lies beyond the detectable universe. What we know, and skeptics would say we think we know, is how the universe began 13.8 billion years ago. According to this theory, it began from an incredibly hot and dense point, known as a singularity. From this proverbial primordial seed, space, time, and matter eventually emerged, and the universe began to expand. And not at a calm pace, but within the framework of an unstable growth called cosmic inflation, which lasted only a tiny fraction of a second. In detail, the universe expanded by a factor of 10 to the power of 26 in this absurdly short time span. In other words, it became 100 quadrillion times more vast than it was before in the blink of an eye. So far, the world agrees, but in the same breath, cosmic inflation also raises at least two central questions. Why did the universe begin to expand exponentially, and why did it stop? Subsequently, is our universe just one among others? Well, to simplify, experts assume that there was, or is, a special field that exerted a significant impact on the inflationary process. This field is called the inflaton field. According to the theory, this field could cause the universe to expand by creating rapid expansion. In the case that the inflaton field was in a false vacuum just after the Big Bang, random quantum fluctuations, tiny random variations in the values of elementary particle fields, could have tipped it into a true vacuum or another false vacuum with lower energy. For better understanding, a true vacuum in this context means a region with minimal energy, but this doesn't necessarily have to be zero energy. In fact, a true vacuum could well contain mass and energy. It simply cannot have a state where this region has less energy, as this would lead to an info void. According to the inflation theory, this means that a shift in the state of the inflaton field triggered the exponential growth of the universe. However, as the field moved from one vacuum state to another, the inflaton field also emitted energy in the form of radiation and matter. This is significant because after this process, the matter now present in the universe slowed down and stabilized the rate of inflation, allowing the universe to later expand at a normal pace. However, some researchers also have their problems with this hypothesis, and this is not a new debate. American physicists Paul Steinhardt and Alexander Vilenkin already proposed in the 1980s the theory that cosmic inflation didn't actually stop completely. In clear terms, random quantum fluctuations could lead to the formation of individual bubbles where the inflaton field would take the right value to trigger inflation elsewhere. And this is a pivotal point. Cosmic inflation would continue uncontrollably. In other words, what we commonly call the universe is actually just a subregion, a bubble, in which our world could expand. Conversely, this theory is accompanied by another compelling idea. If that is truly the case, then there must also be other bubbles in which other universes formed. In this context, the Big Bang would not be the beginning of everything, but merely the start of the cessation of inflation within our cosmic bubble. In fact, in this scenario, there would be no beginning to anything. There would only be an eternal expansion from which new bubbles of universes would constantly emerge, new theories and baby universes colliding with one another. There is no doubt that the conclusions drawn from the bubble model are extremely exciting, but assuming they correspond to reality, is there any way to observe or even contact other universes? The majority of scientists answer this question with a categorical no. We are indeed irreversibly separated from other universes due to the inflationary expansion of space. However, it is worth noting that not all specialists are convinced by the inaccessibility of other worlds. Quite the contrary. In fact, a research team led by Yanamborn and Yoshiyuki Wadabiki arrived at a solution through a study that suggests that it is the interaction with another universe that made our own universe come into being. Essentially, we must not forget one thing. The accelerated expansion of the universe remains one of the greatest mysteries of our time. Let's simply take a look at the puzzling discrepancies in the Hubble constant, which indicates the rate at which the universe is currently expanding. When the corresponding value is determined using cosmic microwave background radiation, the Hubble constant is 67 kilometers per second per megaparsec. However, when the expansion rate is determined using supernovae, red giant stars, anti-gravitational effects, and variable stars, the Hubble constant suddenly rises to 73 kilometers per second per megaparsec. This perplexing discrepancy indicates that the universe is expanding faster than it should, and it has recently been confirmed once again by the James Webb Telescope. To ensure that the data sets from earlier were not erroneous, Webb examined more than 320 Cepheid variables and proved that the impossible discrepancies are real. However, the context of this fact is as uncertain as the answer to the question, what is behind the accelerated expansion of the universe? To explain the cosmic acceleration anomaly and reconcile it with the standard cosmological model, experts have suggested the existence of a mysterious force that opposes gravity, dark energy. However, this hypothetical form of energy has not been directly proven and, so far, it has only been recognized on paper because it stimulates the accelerated expansion of space. This is why some astrophysicists sometimes seriously question the very existence of dark energy and are looking for alternatives to explain the processes of the universe. However, the aforementioned study by Amborn and Wadabiki proves that these alternatives can also be very surprising. Published in the Journal of Cosmology and Astroparticle Physics, it concludes that the expansion of the universe might actually be due to constant interaction with other universes. Furthermore, according to Amborn, this interaction with what are called baby universes might even explain the data gathered better than the standard cosmological model. In principle, the hypothesis that multiple universes interact with ours is not new, but what is new is the mathematical model that inspects the possible effects that such a scenario could have on our world. The researchers' calculations have shown that the combination with other universes would increase the volume of our universe, an effect that could be perceived by our instruments as a cosmic extension. Furthermore, the scientists have also determined the rate of expansion of the universe that would occur in this case, and their results are ultimately more consistent with the actual perceptions in space than the traditional standard cosmological model. Moreover, the authors have also addressed the issue of cosmic inflation in their study, and in doing so, they have moved away from the idea of the inflaton field. Instead, the scientists explained the ultra-rapid expansion of the standard early universe, suggesting that our young universe was absorbed by a larger parent universe. From there, the specialists assumed that our universe continued to crash into other baby universes after its own assimilation, engulfing them in turn. To verify their revolutionary theory, the specialists are currently conducting a series of experiments to uncover the hidden properties of the cosmic background noise and miniature gravitational waves. However, the future will have to show whether the established standard model or the baby universe theory is better suited to describe the current expansion of the universe. Yoshiyuki Wadabiki places all his hopes on the data that the James Webb Telescope and the EU will gather in the future, and we now place all our hopes in the new data that you will gather. I hope you don't hesitate to press the like button and subscribe so you never miss a new video from us.